We've arrived at the hour and people are still coming in, I see, although I've now disabled the beep. So, but I think we should start. It's our great pleasure to have Tilman Pfau visiting us today. So Tilman is a professor of physics in Stuttgart, and he studied and did his PhD and actually also a large deal of his postdoc in Konstanz under the supervision of Jürgen Mlinek. But he also had stays in Paris with Corinne Tanugin at INS Paris, and he was a Theodor Fellow in the group of Wolfgang Ketterle actually at MIT. And this has not been the only time that he's been in the Cambridge area. So he also was the inaugural Alex Dolgano lecturer at Harvard University in 2016, where he also stayed at ITAMP for a couple of months. So Tilman's research is, I think, very broad, and it is, like, for example, spans ultra-cold dipolar atoms, and we'll, I think, hear some of that today, as well as interacting Rydberg atoms, both ultra-cold and hot gases. And so in Tilman's lab, there has, for example, been the first observation of some dipolar effects in a chromium condensate. And also there has been like the first Rydberg excitations of atoms in a quantum gas, and then Tilman and his group observed like first ultra long ranged Rydberg molecules. And all of this work has gained Tilman a couple of prizes. Now I'll just name three that I found very outstanding. It's like the Rudolf Kaiser Award in '98, followed by the 2014 Gentner-Kastler Prize of the Société Française and the German Physical Society, and finally in 2017 the Herbert Breuder Prize of the APS. So I guess today we'll hear a wide range of topics, starting from the observation of droplet crystals in dipolar gas, that's a discovery in Tilman's, or observation in Tilman's lab from 6 years ago, I think now, to super solid phases, and then all the way to a new quantum gas microscopy technique that actually was covered just 3 days ago, and I discovered in physics, in the physics magazine of the APS. So very excited to hear about that. So Tilman, the stage is yours.
Okay, well, thank you very much, Valentin, for that invitation, the introduction. It's a pleasure to be back. I hope I can come in person at some later time again. I really miss the area and all your company that I enjoyed so much during my sabbatical 2016. What I'm going to talk about today is a dipolar supersolid. That's the largest fraction of the talk. And at the end, as you said, as a dessert, let's say, very briefly, I will introduce this new quantum gas microscope or microscopy technique that we have developed. So what I'm showing here are YouTube videos that I stole from that project here, Chemical Bouillon, I guess is the name. They are playing with ferrofluids, okay? Here's another movie that they made, and I will come back to that movie, that particular movie at the end of the talk again. This is how a fluid behaves that has that consists of a colloidal suspension of magnetic particles, and the structures that you see here are induced by ever-changing magnetic fields, so by ever-changing dipolar interactions in that classical fluid. Now, these structures that you have just seen, these so-called labyrinth structures, this kind of morphology is actually fairly widespread in physics. I just copied this figure from a book about morphogenesis, origins of patterns and shapes here, where you see this kind of labyrinth structures that you have just seen in that movie here in garnets, but also in superconductors in a magnetic field. Here is another example of such labyrinth structures. This is lead on copper, on that surface physics. This is soft matter physics. These are mixtures of two different polymers. And then, of course, Langmuir films are also in that class. And I mean, this rich structures here you get in all these different physical systems by an interplay of various interactions. Yeah, short range is SR, LR is a long range interaction, and then there's also some mid-range interaction. And so if you start to play with interactions in such systems, well, you can come up with very rich phenomena. That's basically what you should take from there. And the system we are going to look at in that talk are dipolar quantum fluids. And before we do that, let's look at the classical magnetic ferrofluid again. Here you see a droplet of that fluid. And if we switch on a magnetic field, you see that it actually elongates along the magnetic field line and eventually even splits into many little droplets here. Okay, that's called the Rosensweig instability of a classical ferrofluid. And it comes about due to the interaction of dipolar nature. You know, these black droplets here are full of nanoscopic magnetic particles that are aligned in a magnetic field such that they experience a dipolar interaction. And then in these almost incompressible fluids, there's surface tension and, of course, gravity that pushes this fluid downwards to the surface. And that interplay is already enough to produce these funny systems, funny effects, including the breaking of a translational symmetry of the system due to surface waves. And here's another picture. Actually, this is Rosensweig, who covered that field like 30 years ago, 40 years ago. There's a nice book by him on ferrohydrodynamics. And here you see him playing with this black liquid, which is this ferrofluid. If you put this ferrofluid in a oblate geometry, let's say in a petri dish or so, then you put it into a magnetic field, you start to see that the surface experiences these spikes. Yes, it looks like a hedgehog. Yes, and there's a characteristic period to that. And if you want to describe it in terms of a dispersion relation, that's also in this book here, then it looks like this, that as function of magnetic field, this dispersion relation at a critical length scale or a critical K here softens, the dispersion comes down. And if this dispersion relation hits the zero energy, then it doesn't cost any energy anymore to build structures like this with a given period. And that is a symmetry breaking process that basically breaks the translational symmetry of that otherwise flat surface of the liquid. And it looks like a periodic structure with this characteristic momentum here. Okay. This is basically the analogy of what we will do now in the quantum world. Yes. We will do something like this with a quantum gas. Now, if we want to do so, we have to choose the right kind of atoms, and we have to remember that we have an interplay of these interactions. So in addition to the normal contact interaction that we have in quantum gases, it's described by the S-wave scattering length AS, that is short range and anisotropic. We want to have a dipolar interaction. So we better choose, for example, magnetic atoms that have a large magnetic dipole moment mu, such that the interaction, you know, that is long range, it falls off like 1 over r to the third power, and anisotropic gives rise to, you know, either attractive interactions if they are head to tail, or repulsive interactions if they are side by side. Okay, so that's this y2 spherical harmonic here in the angular dependence. Now that interaction can also be described by a length scale, and that length scale goes like the magnetic moment squared times the mass of the particle. Okay, so if you build the ratio of those two coupling constants, G and GDD for dipole-dipole, we define a dimensionless quantity epsilon dd here, which is nothing else than the ratio of those two length scales, ADD divided by AS for S-wave scattering length. And if you are changing it such that epsilon is 0, well, then you have the normal BEC case with just a contact interaction. And if epsilon dd becomes larger than 1, then it is strongly dipolar, meaning that under the influence of that dipole-dipole interaction, even a three-dimensional system will become unstable due to the attractive nature of that dipolar interaction. That's how the epsilon is defined. At epsilon dd equals to 1, this three-dimensional instability sets on. Now, if you look at the periodic table, you know, what kind of atom do you want to use? Well, you want to use one where this mu squared is as large as possible, okay? And as Valentin mentioned, already more than 20 years ago, I started to work with chromium to observe the first dipolar effects there. But in the meanwhile, after it was demonstrated by Ben Lev, for example, that you can Bose-Einstein condense the lanthanides, we switched the experiment to dysprosium. Actually, it's still the same chromium oven, the same chromium Siemens-Lower and vacuum system. We just exchanged the material and tuned the lasers to the right wavelengths. And of course, you know that there's also erbium here. That's the element that was pioneered in Innsbruck by Francesca Ferlaino's group. And you will hear during the talk also some of her measurements as well. Actually here, for example, so if you think about the dispersion relation of a BEC in a pancake geometry, like depicted here, where you are having a magnetic field that is pointing perpendicular to that pancake, such that the whole pancake is fully magnetized, then if you calculate the dispersion relation, and that was done early on by Luis Santos, Shora Shlapnikov, and Maciek Levenstein, then you see that if this epsilon gets larger, you start to develop a minimum in the dispersion relation at a finite momentum, again, just like in this ferrofluid surface wave case. And if this becomes 0 here, well, then the system can undergo an instability, okay? This dispersion relation was actually recently nicely measured by Bragg spectroscopy in Francesca's group here. Now, what happens, or how can we tune that dispersion relation? Well, we have Feshbach resonances. Yes, in these lanthanides in particular, but also in chromium, we can use Feshbach resonances to change the contact interaction. So not the ADD here, but the S-wave scattering you find in that epsilon dd here. Yes, and so if you start with a large scattering length, let's say with an epsilon dd slightly smaller than 1, and you change the magnetic field, you can tune that dispersion relation such that eventually it hits the 0 here at that roton momentum. Actually, the name roton is just in quotes here. It has nothing to do with rotation and also nothing to do with the direct microscopic physics in helium. It's just the fact that it is a minimum that eventually touches 0 here. And at that point, you would expect a formation of a droplet crystal. However, at the time, you know, that was known fairly early on in the field of dipolar gases. But what people believed up to 5-6 years ago is that as you are working with a very dilute gas, not with a liquid that is incompressible, yes, these droplets that are forming then are even more unstable than the initial state, which was a pancake here, yes? Because now you have many more dipoles head to tail than you had before. So everybody was expecting, if you look at this instability, you would start to see a subsequent collapse of every individual droplet here, okay? Now, when we did this, we tried to see this collapse in 2015. There was a big surprise, yes, because there was no collapse. And no matter what we tried, basically, these droplets always stayed around, and the time scale for that was like hundreds of milliseconds, yes? Whereas the collapse time scale would have been less than 1 millisecond or so, yes? So that was a big surprise. And we didn't, at first, we didn't really understand, but today, of course, we understand this. here are some pictures of these first droplet crystals. They look fairly similar to what I showed you in these classical ferrofluids. But why are they stable? Well, we demonstrated shortly afterwards by scaling by scaling experiments with varying densities and measuring power laws that the stabilizing mechanism in this case comes from the first beyond mean field correction of the Gross-Pitayevsky equation, which goes like the density to the power 3/2, or the modulus of the wave function to the third power. So it scales a little bit higher than the two-body interaction here that goes like psi squared in this formulation here. Okay. Now, these quantum fluctuations are well known, of course, since the 50s. Yes. For contact interaction, that's this term here. And for dipole-dipole interaction, they have been calculated by Pelsa et al. In 2012. Now you have these two interactions, and the trick now is that they both produce a mean field. One is positive and the other one is negative, such that they almost compensate each other, such that the overall mean field is much smaller than every individual contribution. However, the fluctuations, of course, add up in quadrature. So this term then becomes very dominant and very important. And it is this term that stabilizes these, and you should note it's a repulsive term that stabilizes the system against the collapse. Okay. And that makes it possible that within this extended or effective Gross-Pitayevsky equation, you can predict all kinds of new funny things. For example, three-dimensional droplet states, like in a normal liquid, of course, yes, that are stable even without any trap. Although this sample is about 8 orders of magnitude less dense than any other liquid. Yes, it's a dilute quantum gas. Yes, and well, we demonstrated this soon after, also in 2016. We just prepared one of these droplets, switched off all the traps. We levitated it with a magnetic gradient field here, and we could observe those, droplets floating in our vacuum chamber for, in this case, 70 milliseconds. And we could then study, for example, that this stabilization mechanism is really a many-body effect, because if you lose the atoms, for example, due to inelastic three-body collisions, and you go below a critical number, then this droplet will just evaporate back to the gas phase. And we can observe that critical number, and we measured all of that at the time and understood it fairly well. These droplets were later also found in other systems, in erbium, in the Innsbruck group, and also, by the way, in not dipolar systems, but in mixtures of two alkali atoms or isotopes by Letizia Taruel in Barcelona first, and then also by the Fattori group in Florence. And this kind of droplet was actually even predicted in 2015 by Dima Petrov. Okay, so these quantum droplets are stabilized by this repulsive Lee-Huang-Yang correction, and we can now basically describe the dynamics of formation, as you have just seen in that little movie, or all kinds of things about the excitation spectrum and the ground states, as we will see, using that effective theoretical description by the effective Gross-Pitayevsky equation. This whole business about quantum droplets by now is a research topic in its own right. I will not go into detail now here. I want to focus more on droplet arrays, like these ones. What you see here are 4 or 3 droplets in a row. And what you see are many, many pictures as a function of time. You see that they live for many hundred milliseconds. And you can now see, of course, from that data set that there are collective excitations and so on that you can study in these arrays of droplets. Okay. Now, we understood already a few years ago that if you have a single droplet and you play with the confinement along the long axis of that droplet, then this droplet will start to break up into several droplets. That can be shown numerically here on the right side for such a dysprosium gas for our typical parameters. And on the left side, again, for these classical ferrofluids, where you see if you are tuning the dipolar interaction by increasing magnetic field, this one droplet is splitting into many droplets. Okay. Now, this is a periodic arrangement of droplets, but it is, of course, not yet a supersolid, yes, because you see it on the right side on this simulation where the phase of that object is encoded in the color, that the phase of these droplets is, of course, different because they do not have enough overlap and they quickly lose their phase coherence. Okay. So if you, however, imagine now a ground state that looks like this, where you have a, let's say, flat fluid part, psi fluid, and a corrugated solid, in quotes, part, where this state has broken the translational symmetry, and you build a superposition of the two, then this is what I will call a supersolid for the purpose of that talk here. Okay. And you see, of course, this is not a trivial ground state, yes, because that corrugation costs kinetic energy. You can only reach such a state if there is a delicate interplay between kinetic energy and all these interactions, and in this case, also the quantum fluctuation term that I was mentioning. Okay. Now, if you do the calculation with this Kospidayevsky, you see, okay, if you change the scattering length from a large value on the right to a smaller value on the left, then these ground states first look like a flat BEC in a trap, but then they start to develop, in this case, 3 little droplets that stay connected here. There's a background, and that means they will have a link between the droplets, and they can keep the same phase if the temperature is low enough. And on the left side, you see isolated droplets. If the scattering length is too small, that overlap will basically vanish, and you will lose this phase coherence. Okay. If you look in situ, and the lower row are our in situ images of the same situation, you can see that the experiment looks fairly, it looks like predicted by the theory. However, that's not enough, of course, to claim that you have seen a supersolid. We are probing now this coherent crystal with respect to its modulation depth by looking just at in situ images, like on this left side here. And then we just expand the whole cloud and look in time of flight. And then from such a arrangement, of course, you see a diffraction pattern, yes? And from that diffraction pattern in momentum space, and from the statistics of that, you can derive the coherence between the droplets. And if you look closely, you can actually not only see the next neighbor coherence, but also the next nearest neighbor coherence, and so on. So without going into much detail, here are the phase diagrams. Here is the phase diagram that you can just measure. This is an experimentally determined phase diagram by looking at the in situ modulation. On the right side, there's no modulation. That's the BEC at large scattering lengths. Then for various atom numbers on the left side, you see more and more modulation. This is what we would call a droplet array. If you want to know about the coherence, then you have to look at these time of flight images. And if you know, here the color code is phase coherence of the nearest neighbor. And you see that only in the vicinity of that transition here around this point A, for example, you have a dark color, meaning that the coherence is high. Whereas on the left side here, this coherence vanishes again. So here you can clearly separate the coherent droplets from the incoherent or isolated droplets further on the left side from the transition line, which is this dashed line here. So this all agrees reasonably well with theory, and is some evidence for supersolidity in the dipolar quantum gas, but it's still not enough, yes, because you want to also demonstrate that if you perturb the system, that there is some superfluid stiffness or phase rigidity. Okay, so how can we do that? Is this state, I mean, really superfluid if by doing an experiment that not only proves phase coherence, but also this phase rigidity? Well, and for that, we are looking into the collective excitations of the system in a trap. So what you see here on the right side, here is a BEC. That's again the scattering length. And here I just plot the energy of collective excitations. For example, the well-known dipole mode here in units of the trap frequency, which is 30 Hertz. That's the red line. It is independent of the scattering length. And that means that the whole condensate is just shaking back and forth with the trap frequency. Whoops. Then there is an antisymmetric, a symmetric mode, which is the quadrupole mode. So red and blue indicates here symmetric and antisymmetric modes. Now these modes are basically given by the trap, yes, up to some factor, they are given by the trap. But there is this roton now, so there are collective modes that are getting soft as we are coming towards that transition to the supersolid. And this is the finite size version of that roton, basically, that we discussed in the continuum. And if you look at those modes, you see that they are actually degenerate. There is a symmetric and an antisymmetric version of them. That's the symmetric one, and there's the antisymmetric one. And up to the transition point, they are degenerate. I should say this is a calculation now, yes, just to illustrate what we are after now. Now, at the transition point, that theory predicts that as the BEC now gets a structure, you know, the one and the other roton modes start to split at a finite gap, actually here, which corresponds to the emergence of the modulation structure on the surface. And then there is a symmetric wave around that, let's say, 3-droplet state, which is an amplitude mode, the so-called Higgs mode, that quickly rises up here. And there's a low energy Goldstone mode, and that's the interesting one now here, that goes even further down in energy, much lower than the trap frequency, which has an antisymmetric form. Oops, I should. So if you look at this mode, then you see that left and right droplets are exchanging particles via the weak link between the droplets. And you see that there is a movement left to right, but it is such that it does not cost trap potential energy, let's say. That's why this mode can be much lower than the trap frequency itself. In other words, the system is excited, but it keeps the center of mass basically at the origin. Okay, that's the low energy Goldstone mode that now is only possible if there is superfluid flow from one droplet to the other, as you can see here in that little movie. Okay, there are lots of other higher lying modes. I am not commenting on them. And in a nutshell, we have observed that Goldstone mode exactly in the same parameter range where we have seen phase coherence, that's the red curve, where we have seen modulation, that's this blue curve up here. And here in the lower one, you see that we observe a feature that we attribute to the Goldstone mode by looking at in situ pictures like this one up here, where you can see, okay, it's not a symmetric picture. The left droplet is actually higher than the right droplet. And if you observe that many, many times, you can see that the center of mass of that thing is not excited. And you see that the side peaks are going up and down. So with these three observations, namely the in situ observation of the modulation, the phase coherence measurement, and the observation of superfluid stiffness via this low energy phonon mode, this Goldstone mode, we believe that we have now proven that this supersolid state of matter in that system actually exists, and we can move on and look at more fun stuff with this super solid. And then something wonderful happened, namely Martin Zwirlein joined us during his sabbatical. And he was teaching us a lot, in particular about fluctuations and what we should look at if we are looking at our in situ pictures. So if you look at these fluctuations from shot to shot, then of course you can use that to measure the structure factor of the system as a function of the scattering length as you go through that transition, for example. So the structure factor is the Fourier transform of the density-density correlation function, and it has, of course, been very important in the context of superfluid helium. Yes, it was measured by neutron and also by X-ray scattering. And of course, it is also known for normal quantum gases where you can measure it, for example, by Bragg spectroscopy. But what we are going to do is we just look at in situ pictures. Because if we look at in situ pictures, we have simultaneous access to all momenta at finite temperatures. And we are going to define that structure factor by the Fourier transform of the spatial fluctuations. I will come back to that in a minute. And then, of course, this structure factor is also linked to the excitation spectrum. There's this connection between the dispersion relation here and the structure factor, so-called Feynman-Beal formula. And that tells us that if we have a roton minimum that is appearing at a certain momentum, then the structure factor and the fluctuations should actually increase. And if this is touching close to zero, then there will be a huge peak at that momentum where the roton minimum is touching zero. Okay, so this softening can be directly observed in the fluctuations. And is a precursor, of course, of the supersolid phase transition. So in the experiment, what we do is we take hundreds of images, of course, for different scattering lengths in the BEC regime, in the supersolid regime, and in the regime of isolated droplets. So these are these individual pictures, NJ. We take the average of all these pictures, that's this quantity here, and we measure the fluctuations around the mean, delta NJ. Okay, so these are the delta NJ pictures then. So we have lots of them for different scattering lengths again. And you can already see here, these are just single shots, that the fluctuations in this supersolid part actually already looks like the rotons modes that we would expect. So these are sort of direct images of these roton modes. And then what we do is we take the Fourier transform of that, take the modulus square and average it. So that gives us the mean power spectrum for the three different scattering lengths again. And you see already from the color code that fluctuations in the supersolid or close to the transition are, of course, strongly enhanced. So, and then what we can do is we can just plot this structure factor. We just cut what I just showed you as a function of the momentum. So in Fourier space, and we start on the BEC side at large scattering lengths here. Already there, we see a little bit of a hump due to roton population already deep on the BEC side. And we see that this hump is increasing. The roton momentum actually shifts as predicted, yes, by a variational approach to higher values. We see very large fluctuations up. This maximum structure factor is actually on the order of several hundred, which is connected to the roton gap and the temperature like this here. And then at the transition point, we have the maximum value. That's also the inverse spacing of the roton and later on of the droplets. And if we go further, then we see that the structure factor starts to show a splitting in momentum space. And these are the emerging phonon modes of the crystal, actually, because that dashed line, that's the droplet spacing in momentum space, is the edge of the Brillouin zone, if you like. And around that, you get phonon modes that you can directly see here in the structure factor. And the nice thing about this is it is just looking at images directly. There is no, this is model free. Yes, there's no fitting to any theory. This is the bare data basically. Okay, now you can estimate from that the continuous version of the finite size spectrum shown here. By that Feynman-Biel formula, you can just invert it to extract the dispersion relation by assuming a certain temperature, which is 20 nanokelvins in our case. And you can see, and that's again experimental data, just under the assumption of that temperature, that this roton minimum is coming down and that the roton K is getting larger. Yes. And at this point, the transition actually happens. I told you it happens at a finite cap already. And beyond that, basically this single mode approximation that underlies this Feynman-Biel formula is no longer valid. So we cannot continue that extrapolation. I mean, mathematically we can do it, but it's sort of not allowed because you are not only speaking to a single mode anymore. So yeah, this is our way of looking at the roton directly by just looking at the fluctuations. And you can do that also in more dimensions, like in 2 dimensions here, because there you not only have excitations along the chain, you also have, well, you have 2 dimensions. So you have a radial excitation, a radial roton, that's like breathing, for example, and angular rotons. Sorry. That have excitations along the azimuthal angle here. And there are m equals 1, 2, 3, and so on modes. Yes. So what was known, of course, in 2D already since a long time, going back to John Bohn's work here, 2007, is that the ground state, already before it becomes unstable, would form a so-called blood cell shape, which means the ground state would have a little rim here, basically. This is what we also see here in this numerical calculation, that if we reduce the scattering length, we come to that transition point here on the left side. Then we first get this blood cell shape here. And then there are all kinds of excitations on top of that ground state that are sort of softening. Yes. So the dominant soft modes are those 2 modes shown here, m equals 2 and m equals 3 angular roton, whereas the radial roton is actually fairly high up here. Okay. And again, this is the dipole mode. All of this is actually below the gap that is defined by the trap, yes, which is at 40 Hertz in this case. So the question was, can we observe it in the experiment? Well, we do the same procedure. We observe these images, single shots. There, of course, we have arbitrary angles, yes, because this is a symmetric trap, and these droplets can arrange in any orientation, like these 3 or 4 here. But if you take the mean images, well, then this rotational symmetry is smearing out the structure, and you get something that looks like this blood cell actually here. Yes. And then we can compute again the fluctuations around that mean image, just like we did in 1D, and get the structure factor. And here I show you the structure factor first for the, if you do an angular average, so just for the radial direction. And again, we see that this structure factor increases, has a maximum at the transition. That's the relative zero scattering length case here. And then we can follow it even beyond that transition point. So we can also see this shift of the roton momentum that we would expect. And then there's the maximum where we get the transition to the 3 or 4 droplet crystal. Yeah. But this is finite temperature, so strong thermal fluctuations are here and is driving this transition to the crystal. Yes. Now we can also look at the angular rotons. So this means we are now plotting this as a function of theta. And again, look at what happens. And then you see that at the transition, we start to see a dominant feature of m equals 2 and m equals 3 angular rotons. Here is are the Fourier components basically that we see. And around that transition, that's this gray area, these guys have a maximum. Okay, so basically what it means is that in 2D, you can observe these softening modes in the radial direction, but the first ones that you actually see more prominently are the ones in the angular direction, because they have a lower energy. Okay, so what does it mean for supersolidity in 2D? Well, there's a clear path, yes? I mean, there's again the transition from this blood cell shape to something that has a modulation structure on top of that rim, that eventually, if you go too far in the lowering of the scattering length, will lead to separated, isolated droplets that lose their phase coherence. And you can study this, of course, again, with the Bogoliubov-Dechaine analysis for these finite modes. You can study also what it means to have a Goldstone mode here, as you have a rotational symmetry, a continuous symmetry. Here, the Goldstone mode can be actually strictly at 0. And there's a Higgs mode again that shoots up. Well, in a nutshell, here you can actually, in the theory, measure the overlap between the droplets. So you can see that there is a phase transition happening here, and there's a finite overlap. And we also checked that this should be possible with a dynamic preparation sequence. And that's what we are working on right now to basically demonstrate that formation of that phase coherent supersolid crystal in 2 dimensions as well. Now, if you have that theoretical tool at hand, then you can do something that is not so easy in the experiment. Namely, you can just increase the atom number. Yes. And what I do here is just show you the ground states of that dipolar gas as I increase the atom number. Okay. In the very beginning, maybe I should go back. What you saw here was very quickly this 3 or 4 droplet crystal. Yes, but you see that if you increase the atom number further, then funny things happen. Yes, and I show this to you for 2 different scattering lengths. Sorry. And now you maybe remember these movies that I showed you at the very beginning that have this labyrinth phase here. Yes, which means that these structures here show a huge degeneracy. Yes, there's no clear ground state. All these labyrinth structures have almost the same energy. And here we have mapped out a phase diagram as function of atom number and scattering length for such a cylindrically symmetric oblate 2-dimensional dipolar supersolid. At large scattering length, we have a BEC. Here we have at small atom numbers these droplet crystals that I was describing. Yes, 3 or 4 droplets. But if you then increase the atom number, then you see a lot of more things happening. Yes, like for example these inverse structures. Yes, and a superfluid where you punch a lot of holes. Yes, in a regular pattern. Remember, this is a ground state. Yes, the flow field is 0. There's no flux here. Yes, but still the dipolar interaction punches these holes, and the reason for that is that, again, due to the stabilization by the quantum fluctuations, the density of that liquid is eventually limited. It's like a real liquid, which is almost incompressible, basically. Yes, and so if you add atoms, you can add only so many atoms until the density hits a certain limit, and from that point on, the system can only minimize its energy by forming these crazy shapes, basically. Okay, that brings me to that movie again, yeah, that I showed you at the beginning. It would be fantastic to see such a fluid forming but not only as a classical fluid like here, but as a superfluid, yes, where you can study all the excitations again, and you can ask what are the what are the quantum properties of that substance. Okay, so that brings me, I'm not sure what is the time here. That brings me to the end of the first part of the talk. And I really want to thank Martin, of course, Martin, for spending so much time with us in contributing many crucial ideas to what I just showed you. Hans-Peter, my friend and theory colleague in my department, that is also a great guy to talk to and get advice on these funny states of matter. Then, of course, Tim Langen, who is a senior scientist in my group, and all the group here. I want to maybe particularly mention Jens Hertkorn. He was a master student. Now he's a PhD student. And a lot of these theoretical calculations that you have seen have been done in his master thesis. All right, that concludes the dipolar part, but I have maybe 5 more minutes, or Valentin?
Yeah, that sounds about right. Do you want to maybe take questions now on this part, or you think like it's more coherent to first go through the
Let me just do these 5 minutes, and then we can take questions to everything at the end.
Sounds good.
It's going to be quick. It's now a different experiment. Yes.
Sure.
Here we are preparing a quantum gas in a chamber that maybe lives in an optical lattice, has a structure, and we ask ourselves, how can we observe individual particles in that bulk material, let's say. Yes. And the way we do it is we excite to the Rydberg state or ionize at some time. Then we can, in principle, have a wait time and then extract those ions and magnify the ion image here by a factor of 1,500 roughly on a multi-channel plate, and then look at what we get. Yes, and you know these multi-channel plates can have quantum efficiencies up to 85%. So you can see almost every atom, not every atom, but almost every atom. So we have realized this, and of course, if you have an ionizing process, for example, laser excitation, or the field ionization of a Rydberg atom, you can produce very cold ions and observe them now with very high resolution. And the resolution that we have demonstrated with this 3-lens ion microscope that you see here, that was actually it's a self-built ion microscope here, that has a magnification, as I said, up to 1,500, delivers pictures like this. Yes, so that's an optical lattice just for test purposes. Here it has a period of 532. By now we have a lattice period, actually I forgot to put the picture in, that has 240 nanometers, and we can still resolve it. And the nice thing about the ion microscope is now that it has an extremely large field of view transversally, and it has an extremely large depth of field. For example, in this particular measurement, we demonstrate a depth of field of 70 micrometers. Yes, because we are taking these ions and we are basically just extracting them and project them on the MCP. Yes. So the usual limits of a quantum gas microscope in the limited field of the depth of field basically is absent here. So this is just to advertise. This is a new tool for us. We can also do it in pulsed operation, such that we can excite in zero field Rydberg atoms or ions, and then only pulse it on and image it. And if we then use the time of flight information from the moment we pulse on the microscope to the detector, we can also get 3-dimensional images, as shown on the lower right here. It's just a test image at this point. Yes. So this tool, I think, could be very interesting for future applications in bulk quantum gases. to measure correlation functions, anything that is interesting on that length scale of the resolution, which is about 200 nanometers at the moment. For example, how ionic impurities will form, or how in the Fermi gas Friedel oscillations would look like, or how Rydberg correlations or ion-atom collisions actually happen. But this is a new tool. I'm also very interested in your suggestions what to do with this tool otherwise. Okay, so that was just a quick 5 minutes presentation of our ion microscope. And with this, I thank you for your attention. And I'm happy to answer any questions that you might have at this point.
Well, first of all, thank you very much for this very nice talk. I'm sure there are questions and we have some time for those. So like we normally do this in a very informal way. So you just unmute your microphone and speak.
I've got a question. Thank you for the very interesting talk, Tilman. For the ion microscope, are you at some point limited by Coulomb charge density for being able to ionize the entire quantum gas with, and then you're limited by the Coulomb repulsion between your ions?
Eventually, yes, but you know, the time of flight from the sample to the MCP, which is actually 1.5 meters higher, is a few microseconds. So if you are working on time scales that are longer than a few microseconds, then you are not running into that problem. Yes.
Okay, so I guess in other words, by the time that your ions get to your MCP, they may have moved a little bit relative to one another via Coulomb repulsion, but then the spatial structure is
if two of them would travel together within a time window that is, let's say, a few nanoseconds or so, yes, then they would affect each other, yes. So your ionization rate has to be lower than that gigahertz, basically, but that's not a limit really for the most part.
Okay, thank you.
A more severe limit, if we discuss this, if you're interested in that, is the quantum efficiency, which of course is not as good as any regular quantum gas microscope, yes, which works with fluorescence, and that can be much more efficient. So we are currently, right now in the lab, actually working on a method to increase that quantum efficiency by taking one ion, excite a Rydberg atom around that ion by the so-called anti-blockade, and then first send this first ion to the detector and then a second one behind and maybe a third one behind and so on, such that we can sort of pre-amplify the first initial ion in the cloud and then extract it to the detector. And then, of course, if you have that gain, you can increase the effective quantum efficiency per ion dramatically.
So there is actually a question in the chat from Fermi3 controller. So that says, like, thank you for the amazing talk. What causes the labyrinth patterns to be asymmetric, really, radially?
Yeah, that's a good question. So I mean, you are talking about those structures here, right? And yes, yes. And I mean, this is just one realization. Yes, if you do this calculation here in imaginary time propagation many times, then you get different patterns anytime you do it. Yes, so it means there's a very large degeneracy between many configurations here. Yes, and these are just examples basically of how they look like, and that's intrinsic to those you know, systems that have that labyrinth type of morphology. That there's a huge degeneracy basically between all these options.
But maybe to follow up on this, like actually when you go into these states with a higher angular momentum, so I guess that's the kind of the same thing. Like if I really evolve the system, then I get a superposition of these two states, maybe plus plus m minus m, but then when you project, like you get one of them. Is that how I can understand it also?
Now you talk about
these blood cells that were
these modes here, yes?
Yes, exactly.
So here I should say, this data, before we are plotting it, is already rotated, okay? So we are aligning all the images such that, you know, the largest droplet basically coincides. Otherwise, the structure would be washed out here, yes? Right, so we are only measuring this relative to the droplet structure that we have in these pictures.
But
there is a large degeneracy that, of course, these droplets can form with any angle, of course. Yes, that's a continuous symmetry still.
But it does it have an angular momentum, these states? Like
these, no, well, I mean, so these in a way it's a superposition of two angular momenta. It's a standing wave in this azimuthal angle. Yes?
Right. Okay, that's right. Any more questions? Please speak.
Yeah, I would have a question on the Goldstone modes you showed. So in the 2D case, you showed that the Goldstone mode is really exactly 0, basically. Whereas in the 1D case, even though it's very small compared to the trap frequency, it's still always a little bit gapped. Is this only due to the presence of the trap, or is there some more fundamental to it?
Okay, that's a very good question. Yes, let's go back. Oh no, it takes a long time. Yes, I mean, this is a finite size system. Yes, and if we would go to an infinite system, then this gap would actually vanish. Yes, where was it? Okay, here. Yeah. So this point here, you know, would move to 0 here, yes, because in an infinite system, there wouldn't be any energy cost basically for that Goldstone mode, yes.
Yeah.
For k equals, I mean, for k going to 0 as well, yes. But here, anything that you do, I mean, has a finite k, yes.
I see. And in a 2D case, this does not happen because it's kind of a spherical continuous symmetry,
exactly,
basically.
Yes.
Yes.
It only happens for the excitations on that rim, yes. If you were to look into the similar structure, which you can actually also do in the radial direction, yes, you can also assign modes that you would call Goldstone and Higgs modes, then they would have a gap again, yes.
Tilman, just out of curiosity, what would limit the quantum efficiency for the detection of ions? I'd always assumed if you had a charged particle like an ion, you could just accelerate it, slam it into some electron multiplier and get close to 100%.
Well, you get, it depends on, so you get up to 85%. That's what the company would specify. They have a certain coating, but then the MCP itself is the problem, yes? I mean, you know, they have holes, but there's some stuff between the holes, yes? And so only the ions that really make it into the hole will be multiplied, yes? And the ones that are not really hitting at the right places, so there's a geometrical limitation, ultimately, I would think, yes?
But if you take a photomultiplier and remove the photocathode, you then have the dinodes which do the electron amplification.
Yes, but then you lose the spatial resolution. Yeah, yeah.
Yeah, so if you would slam the, sure.
I mean, I want to keep the spatial resolution. I need these the channels, the 50 micrometer resolution that I get, you know, is just the size of the whole of the multi-channel plate. Yes.
Could you get the resolution by scanning the ion beam? If you were to focused ion beam and scan it, then you don't need the resolution in the ion detection. But
in principle, that could be done, I guess. Yes. You have to just scan it very fast. Yes, but so but you would still need something, you know, that defines a slit or something that defines it. Yeah, so I'm not sure whether you can actually gain. I mean, you want to detect every ion, not just you don't want to just have a large spatial resolution. You want to also have a quantum efficiency for every ion. Yes, and if you are steering the ions as they move up the column, some of them hit your dynode, yes, no, but the other ones will miss it.
Tilman, it's a highly idealized and probably practical situation. If you're the 2D quantum gas and you would hit with a tightly focused ion beam just one spot and then detect all the ions. And then you go to the next spot. And then you go to the next spot.
This you can do, but but then you are limited by the optical resolution and also by the optical depth of field again, yes?
Yeah.
Which was the motivation here, actually. We get 200 nanometers resolution, but 70 micrometers depth of field.
Cool. Okay. Thanks.
I have maybe a naive question regarding the experiment. When you transition from the BEC to like these droplet clusters, do you do that by various runs, or do you continuously change the scattering length so that you can like slowly go into this regime?
Yeah, so the typical sequence is that we start with some scattering lengths on the BEC side, then we ramp it slowly, let's say in 30 milliseconds to the final value. Then we have a hold time, we wait, and then we take a picture.
Mm-hmm. So when you you drive into this regime where there's maybe like isolated clusters or droplets, what's like the mechanism that makes you lose coherence between the different droplets, and on what timescale does that happen?
Yeah, this happens. I mean, you have seen it in this one simulation that happens fairly quickly. Yes. First of all, the local chemical potential is different. Yes. So in a trap anyway. Yes. The atom number in every droplet is different. So they quickly, if they cannot exchange particles, they quickly, and the time scale is on the millisecond time scale, basically, they quickly start to lose their phase relation. And only if they have a finite overlap and they can constantly exchange on that time scale, actually, particles, then their phase can be maintained.
Okay, cool. Thanks.
So, I mean, theoretically, this is, of course, within our theory, yes, which is an effective mean field theory, there will always be a finite overlap, yes. Yeah. The theory is not capable of predicting anything else, yes.
Right.
However, in practice, then, the dynamics, basically, of the change of the scattering length, for example, is a quench, yes, and it puts in some energy, and you want to distribute that or dissipate that energy, and for that you need the connection, basically.
Right. Mm-hmm. Thank you. Are there more questions?
I've got a last question. Tilman, I don't think you showed any time dynamics of, for example, the Goldstone mode oscillations in these dipolar gases. Is that not feasible to do with this kind of platform, or?
So actually the Goldstone mode measurements that I showed you were not dynamical measurements. These were just shots, basically, after a certain hold time. And basically, this Goldstone mode, the frequency of that Goldstone mode was so low that we just catch the oscillation at different phases every time we do it, but at random phases, let's say. Yes, but still we could see this correlation between the displacement of the central droplet and the population of the side droplets, which correspond to exactly the pattern of that Goldstone mode. Now, more recently, and you see some data here, we can follow this up to much longer times. And we can also study, in principle, collective dynamics and frequencies as a function of time. Yes. so that became possible over the recent year or year and a half. Yeah.
Mm-hmm. Okay, thank you.
Okay, I think we've had plenty of questions, but if there's one more, I'll give the chance. If not, and there still maybe is like an urgent question, I can point out that there is still like one open, like the very last discussion slot with Tilman is still open. So if you want to keep him awake late at night in Europe, then you could take that slot and email me, and I will put you in like on the Zoom list. Okay, for now, before we thank Tilman once again, I would just want to announce that in 2 weeks' time from now, on March 11th, we'll have the next talk given by Michael Köhl. Yeah, please join for that. And with this, thanks again, Tilman, for this very nice talk. Yes, we'll close the session.
Yeah, thanks to all of you for listening and for your questions. It was a very nice discussion.